Maybe I'll spend a couple of minutes talking about some material that you probably need for the first assignment, just to bring you back up to speed. A prerequisite for this class is GSci 452. My guess is that if you don't have that, you can probably survive in this class just fine. But some of the material that you would have seen in that, you will need for the first assignment, and we will cover it again. You may recall that in that class, you would have talked about Darcy's law. And Darcy's law would look something like, whoops, like this, where volumetric flow rates, so it's based around the idea that if you had a core, and if you had a pressure gradient along that core, or a head gradient along some length of that core, and it had a cross-sectional area, and it had a volumetric flow rate Q. Volumetric flow rate, cross-sectional area, hydraulic conductivity is the property of the material. And that the flow rate is proportional to the gradient of the head drop along it, the pressure drop if you like, but it's not, it's a head, it's units of length, so it has no dimensions. And the scaling parameter that defines how quickly flow will occur as a volume flow rate is called the hydraulic conductivity. And so depending on whether you're working as a groundwater hydrologist or as a petroleum engineer, you will use either hydraulic conductivity, if you're a hydrologist, or if, as some of you might be taking the soil physics class, if you're a soil physicist, you're probably working in terms of hydraulic conductivity, where the hydraulic conductivity has units of velocity, length over time. And if you are a petroleum engineer, then you'd probably use the property called permeability. Sometimes hydraulic conductivity is called coefficient of permeability. But not permeability, because as you see they have different units. The units of permeability are length squared. And those properties, either permeability or hydraulic conductivity, are linked to each other through this relationship, where this is the dynamic viscosity of the water, this is gravitational acceleration, and this is density of the fluid, the water in this particular case. And so you can always move between hydraulic conductivity and permeability just by knowing this relationship, always. The reason that petroleum engineers use permeability rather than hydraulic conductivity is that the measurements of hydraulic conductivity are a function of temperature, because it includes how viscous the water is in the measurement. You do the measurement at a certain temperature. If it's a very high temperature, the water will be less viscous, and therefore the volumetric flow rate for given pressure drop will be larger. And so it'll measure a larger permeability, hydraulic conductivity. Permeability is independent of temperature because the viscosity term is included below it. And so that's the reason for this. If you want to get Darcy velocity, the Darcy velocity from Darcy's law, I guess, did we call this Darcy's law? The Darcy velocity is equal to the volumetric flow rate, Q, meters cubed per second, divided by area. The cross-sectional area of this core, in other words. So if you have volume per unit time divided by area, you end up with length per unit time. And so you end up with the Darcy velocity. You could also get it just by dividing this relationship by A, in which case you end up with this. The reason for the negative sign, you know, right? Because if you look at drawing this as a graph, where this is the x direction and this is head, this is a positive gradient, and the velocity that comes out of here is in the negative x direction. So the velocity is really a vectoral quantity, it's not a scalar, and so the negative sign just takes care of that. Yep.
Say you're solving for k, and it comes out negative.
No, ignore it. Just make it positive. Just means you got your directions wrong on your gradient. So there are two velocities that we can think of. This is the bulk velocity that comes out of it. This is the velocity, if you like, of a particle of water. So in other words, if you look at the cross-sectional area of this tube, and you imagine that in that tube you have a whole bunch of grains that fill up a lot of the space in this tube. Not a very good drawing, I don't think. Where the volume of the voids and the volume of the solid and the total volume, which is equal to the volume of the solid grains plus the volume of the voids. In other words, this is these are areas, I guess, in this particular section. These allow us to define a porosity, which we'll talk about. And the porosity is just equal to the volume of the void space divided by the total volume, which is the same from what we just wrote below. Total volume is just this. And so this is the volume of the voids plus the volume of the solid. And so this is important because if the fluid is only flowing within the void space and you have a volumetric flow rate, then the actual velocity that a particle of fluid will be traveling with along its flow line is going to be much faster than you'd get from the Darcy velocity. So if you divide the Darcy velocity here by the porosity, then say if there's 10% of this space is open and 90% is closed, that means that the actual velocity the water is flowing at, the particle of water or contaminants being carried downstream, would be traveling 10 times faster than the Darcy velocity. And so that's important. And it's important because if, for instance, we wanted to calculate how quickly stuff would travel downstream, it's just like going from A to B in a car, and your first assignment is basically to do this, is if you had a contaminant that existed upstream at some location, and you want to know how long it will take to end up at some compliance point which is a kilometer downstream, then if you could calculate the Darcy velocity, for instance, if you knew what the difference in head was between the upstream and the downstream. So this is delta x, if you like. Then you could write Darcy's law as we just have, as equal to hydraulic conductivity, a minus sign if we want it, a change in head that occurs over a change in length. If you know what each of these are, and you know what this is, you can calculate what the Darcy velocity is. But if you use velocity is equal to length over time, and you rearrange that to find out how long it will take for something to travel a given length, these two are related to each other, right? Just rearranged. You can calculate how long it would take to arrive. You know it has to travel a kilometer. You know that the velocity at which it moves downstream. This velocity has to be the advective velocity, the velocity at which particles are moving at. And so if you don't do that, you'd be off by a factor of 10. And so your first assignment is actually to do the residence time calculation for breakthrough at what was the nation's high-level radioactive waste site at Yucca Mountain before it changed, as you'd have seen in the little narrative last week, and to calculate how long it takes to arrive at this downstream location. And so if you start it at upstream at some time 0 and you wait downstream for it to arrive, then all of a sudden it would arrive in 100% concentration at some residence time. And you can calculate that straightforwardly just from velocity is equal to length over time. And so that's one thing that perhaps you need to absorb before you move ahead. Okay? So remember Darcy's law. Remember the difference between permeability and hydraulic conductivity, how you convert between them, and also the importance of understanding the difference between Darcy velocity and advective velocity, because they're key differences. Okay? I think actually for the first 3 assignments, they're actually step-by-step kind of solutions for it. 2 years ago, I seem to remember we flipped the classroom. Flipping the classroom was that we had the students look at the videos beforehand, come to class prepared, and we'd talk about stuff that they didn't understand and go through the assignments. Invariably what it came down to was 2 people came who looked at the stuff, and everyone else came because they wanted to figure out, be told how to do the assignments. It didn't work very well. So we finished doing that. It wasn't particularly successful. So that was my one foray, if you like, into flipping the classroom. All right, so that's the material for the first one. So this class revolves around contaminant hydrology, the rates at which contaminants are mobilized in the subsurface and how they are potentially attenuated. We focus on immiscible fluids because they're the most difficult ones to deal with, either as lighter than water or denser than water fluids. And we deal first with immiscible transport to understand exactly where those fluids will go, maybe within the first 2 months of their lifetime in the subsurface, before they do things like sorb onto solid media, before they dissolve in water and get carried away by the advective flux. And so our first order of business is to be able to understand exactly how these fluids behave in the subsurface as separate fluids. And so the stuff that we'll go through today is just the material that's written on this. Okay. So we'll talk by defining exactly what immiscible transport is. We'll talk about how it's controlled by interfacial tension, which is important. Interfacial tension both on surfaces of grains and in ensembles of grains, and how we can represent that by simple models, some of which we've seen if you remember the second time we met in EME 303 when we talked about capillary tubes, and also when we talked about more complicated geometries. So that's where we're going with this. So there are 2 basic classifications of fluids, those which are lighter than water and those which are denser than water. For those that are lighter than water, if you split it at the surface, then what it will do is it will go down towards the groundwater table. It will be carried down by its own self-weight in this unsaturated or partially saturated zone, and ultimately it will stop when it hits the water table, and it will slightly depress the water table and create a zone in which it gets basically cupped by the material around it. And it's cupped because it's less dense than water, and therefore the water table underneath it is able to hold it. What it will do is it will leave this smear zone as it goes down here, which will be partly air-filled, partly very small amount of water, and partly smeared with the gasoline or whatever it is that went down through here. This stuff will volatilize and be carried off in the air phase. And once it's sitting here, nothing will happen with it unless the water table rises or falls, in which case it will carry it up or down with it, or unless it dissolves in the water which surrounds it and gets carried off in dissolved form to some location downstream and will create some kind of plume as it emanates downstream. So that's kind of the mechanism. So once it gets into the system, maybe this happens within the first few months, it'll sit there and it will act as a source. And so what we need to do is know something about what the morphology of this is. What's it look like? What are the characteristics of this chimney, which is partially saturated, and this lens, which might be close to 100% saturated with the contaminant? And then what happens with it as water flows past it and it gets carried downstream to some compliance point. If it sits here and doesn't move, it's perhaps not much of a problem, or not so much of a problem, but you'd still probably have to, under current regulations, take it out. But we want to be able to understand exactly what controls the shape of this, what stops it from going any deeper, what controls the saturation in this, which will be the source of this off-gassing. When rain falls on this and washes this out, what are the rates at which this will wash out into the subsurface and will also end up finding its way into the groundwater. So those are the basic questions that we'd like to address. We know that one basic form of behavior is for fluids that are lighter than water. If we look at fluids which are denser than water, like dry cleaning solids, fluids rather, not solids, then they have fundamentally a different behavior. And that different behavior is that when they're spilled, they'll also travel under their own weight to the water table, but the water table doesn't act as much of an impediment to stopping them. And so they'll keep on going until something else happens. And the question is, what is the something else that causes it to stop at some location? And typically it'll be an area of low permeability, but it's not the mechanism of permeability which is stopping it. It's the mechanism that, because low permeability materials typically have very small pore throats, that interfacial tension doesn't allow it to get pushed into this region. And so typically a capillary barrier will be what will stop it. It will have very similar properties to the lighter than water fluid, in that this will be a chimney which is smeared with the dense non-aqueous phase liquid, DNAPL. And this will be a zone which is at relatively high saturation in some kind of lens that sits here. You'll notice that the direction in which this lens is moving is not in the same direction as the slope of the groundwater table, whereas in this case the direction in which the lens might try and move on the surface of the water table is along the incline of this. And so it will tend to go in the direction that this sloping surface will define. It won't go very far typically, and it will act as a source so that groundwater which is flowing past this will pick it up, and it will create a plume that gets carried down gradient in the same way as it was in the lighter than water case. And so that's kind of the system that we're looking at. So typical geometries of these depend on the material that it goes into, but this is basically the idea. This, of course, if this is the water table here, and the fact that this stuff has gone across the water table, this has to be DNAPL, right, by definition. Otherwise it would have stopped at this location here. And it's left some kind of sinuous trace that is a smear zone, so that any flow through here will pick up this component and carry it downstream. Some of these will have these lenses that will develop either at a capillary barrier here, or where it reaches kind of minor capillary barriers, which might be low permeability lenses. Or there might be none of those lenses and it just runs out of steam because there's not enough liquid being supplied that it kind of peters out. And so all of these geometries with this kind of cascading structure, it's important to understand why it takes that geometry. And so that's what we'd like to be able to find out, the mechanisms by which it has this geometry and it develops. The other way to look at this, if I can look at this, is if you, for instance, went to a portion of this and say looked at a little box that was here to try and find out why it was pooling. So I guess actually it would really be maybe this point here, why it was pooling in this particular location, that it's partially saturated here and then it doesn't go any further. Then one way to think about that would be in looking at this particular geometry. And so all this is, the red stuff is a non-aqueous phase liquid, something that doesn't dissolve in water. Could be dense, or no, it has to be dense, right? Because it's in water. And if you can see this, then the bead pack, which is here, is relatively fine-grained, and the bead pack, which is here, is relatively coarse-grained. So it's been able to get through this, but where it meets this interface between these two, which is somewhere along here, it's no longer to go across here, except in these tiny little sinuous ganglia, where presumably it's finding a pathway through there where the openings are large enough for it to be able to get through there. And the only physical force that is pushing it through this is the weight of itself pushing down here. It's not being driven by any pressure other than its own self-weight. And so what we'd like to do is be able to understand something about what the controls are in why some of this has gone through here and some of it has not gone through here. And so that's what we'll spend the rest of today messing around with. I won't go through that because we don't need to. So that's basically our task for today. There are some texts on reserve in the library if you choose to look at them. I think the material that you have that's served up in this class is adequate, hopefully, for you to understand the main concept, so I don't think you need to go there. But this one text by Jacob Baer is kind of a graduate level text, but most of the notes that we use for this first part come from there. So if you feel as if you want to get some more knowledge, then that's where to go. Okay. So we've talked about these two systems. One is where the stuff goes after the first month and then sits in place at rest. And then after that it gets dissolved and carried away in miscible form. So the first behavior that we're talking about is immiscible displacement, where it goes as a separate fluid and does not dissolve. And then once it's in place, then it can dissolve and be miscible. And so when we talk about immiscible fluids, we're talking about the motion of two fluids simultaneously, typically water and the NAPL, non-aqueous phase liquid. They move independently of each other, and they will maintain a Capri pressure difference between each other. So in other words, the pressures in the two fluids adjacent to each other will actually be slightly different. And they'll be different by the surface tension and also by the size of the pores within the medium. And so that's what our first task is, to understand exactly how that behaves. The context that we're thinking of that in this case is really oil and water. So oil would be a non-aqueous fluid with water, an aqueous fluid. But the behavior that we see is also exactly the same as in the vadose zone. And so where you have water with air both occupying the pore space above the water table, the behavior in that zone is exactly the same as oil and water below it. And so the same equations apply. And we're talking about behavior which is immiscible, which is the most difficult case. And later we'll talk about miscible displacement. So miscible displacement is where you take a blob of ink and put it in a beaker of milk. And if you drew a cross-section across that ink blob and drew its concentration initially, it would look like this. And if you came back in 3 minutes, it would be spread out, and the concentration wouldn't be so high in the middle, and it would be this kind of Gaussian distribution. And so over time it would just flatten out, and ultimately it would be, if it's blue ink, it would be light blue milk at some stage. And so that is not what we're talking about now. This is what happens once it gets into its place and dissolves in water. We're interested now only in what it will look like and the morphology of it when it goes first in. So it'll have a lens that's here, it'll be cupped by the water table, which it will sit on top of, and it will have a smeared zone above it. If it's denser than water, it won't stop at the water table, it'll just keep on going. It'll be stopped by a Capri barrier, and again you'll have this smear zone. And what we'd like to know is how much of it is present here, how quickly it can vaporize and get into the atmosphere which we breathe, and how quickly it can be carried downstream. So that's our first task. So some definitions, I guess. Interfacial tension and Capri pressure. So we've used already the term saturation, and you probably know what that physically means. It's how much of the pore space is filled with a certain component. So saturation by definition is the volume of fluid that you have within the reservoir, or an aquifer, I guess in our particular case, divided by the volume of the void space. So if the aquifer is completely filled with water, then the saturation is 100% of water. If it's 50% of the void space is filled with water and 50% is filled with air, then it's 50% water saturated, 50% air saturated. So by definition, saturation refers to the volume of fluid relative to the volume of voids. We can talk about the saturation of a particular phase, air or water saturation or NAPL saturation, in which case it's the volume of that particular fluid relative to all of the voids within the representative elemental volume. Representative elemental volume. Not a word you really need to know, but one that's quite used in ground hydrology. It just says that you take a large enough volume of your aquifer that includes enough grains and enough pores that it's representative of the portion of the aquifer next to it. And so as you get a bigger and bigger portion, the porosity and the properties of that control volume don't really change. We know that if we sum up all the saturations, they have to sum to 1. So if it's 50% water saturated, 25% air saturated, and 25% napple saturated, those all have to add up to a decimal 1 or 100%. And so that always has to be the case. We should be aware that saturation is a term that really came out of the petroleum industry. And if you look at other branches of groundwater hydrology, for instance, soil physicists and sometimes groundwater hydrologists, their definition of volumetric moisture content is sometimes slightly different. And it's different in that it talks about the volume of that fluid divided by the total volume, not the volume of voids. And so just it's different by terminology. How many people are, by the way, taking this class in soil physics this semester? So you'll get exposed to it. I don't know what the number is. I think it's probably a bit like this class, but so anyway, so I don't know if that's good or bad for you. And so the other definition of moisture content is by weight in soil mechanics. But the one that we'll use most is saturation, and the one that we'll use is volumetric moisture content slightly when we talk about vadose zone, but most of the time we'll use saturation. Okay, so that's by definition. I'm not going to go through this. So we talked about this property that we'd like to understand, and that is what this morphology of this tunnel, the chimney rather, which is smeared that goes down to the water table, looks like. And the only motive force that's causing that stuff to move is its own weight. It's not driven by any kind of pressure. It's just like dropping a ball on the floor. It's not accelerating, it's moving relatively slowly, so it's just its own potential energy that is causing it to move. So what we can do is we can define behavior in terms of interfacial tension between two fluids, which is this sigma ik, and we can define it in terms of the surface tension. The surface tension is what an insect would feel as it walked across the surface of a pond with vapor, water vapor above the surface of that pond as it struggles across that surface. It'd feel the surface tension of that in contact with its vapor. And we can define Dupre's formula, which says how much work you have to apply to pull together two fluids and separate them into two separate fluids with the combined vapor interfacial tension between them. And so if you take two fluids and pull them apart, the work that you have to do to pull them apart is defined in terms of the surface tension each of those fluids, that fluid with its own vapor above it, and the interfacial tension between those two fluids. So in other words, the tension between water and oil, if they were in contact when you pull them apart. And so it's important to understand that, because if you think about the behavior of multiple fluids, the easiest way to think about them is, first of all, outside the aquifer, where there are no grains to mess things up. And so if you take a lake and you wanted to put gasoline on top of that lake, or that bucket, I guess would be a bit less antisocial, you know that the gasoline would float on the water, and it would have air, gasoline, water in that order, because of the relative densities of these. If you took a liquid where the gasoline was, say, just a small droplet, and you put it on, then that liquid would form a lens, kind of exaggerated here. So this could be gasoline. And if it's being placed on top of water, you could do a very simple free body diagram to represent that behavior. And the behavior would be a lens of this gasoline, air above it, water below it, and you could look at the triple junction between those, and you could draw tangents to that little lens, and the forces that are acting at that little boundary in these three different directions would be the interfacial tension between the gas and the liquid B, which is this. The interfacial tension between the gas and liquid A, which is this. And the interfacial tension between the two liquids, the gasoline and the water, in this particular case, in terms of this. And so, if this force towards your left, my left and your left, is larger than the sum of these two other forces, then that interface will physically scoot across and it will completely cover this boundary. And so you know that's kind of what happens if you put gasoline on top of water. Then if you knew what this physical property was relative to these two other physical properties, you could look for the case where in the limit, instead of being this triple diagram with these angles that are associated with them, if these angles go to basically 0 because it's very flat, then it would just be, this would be the expression that you'd be figuring out what the equality was. And if this force, this material property, giving this force, is larger than some of these two forces, then you'd know that it would spread right the way across the surface, and it would be completely, there'd be a monomolecular layer of gasoline, which would be this sheen on top of the water, which is exactly what you see in reality. So that's the first premise that we are interested to know about. So this is defined purely in terms of these material properties for this particular system. But we're not interested in the behavior for these systems in isolation. We're interested in what they look like when we put them together with a bead pack. And so the system that we'd like to understand something about is what happens when it's present with an extra component. That extra component would be glass beads or quartz, which is basically glass, and to understand exactly what happens in that particular circumstance. So that's the next thing. So let's enter into this by taking the system, and instead of having it a liquid, a gas, and a second liquid introduced, let's have a solid, a gas, and a liquid introduced on top of the solid. We can do the same kind of analysis. We can have a force that acts between the solid and the liquid, a force that acts between the liquid and the gas, and a force that acts between the gas and the solid. We can allow this angle theta to basically go to 0, in which case we don't have to worry about the cosines of this. So if theta goes to 0, then cosine theta goes to 1. And we can do this same calculation again. And so now what we can do is we can figure out, by looking at, say, a droplet of a liquid that sits on this flat substrate of quartz, we could say something about the behavior of this fluid and what we'd expect it to do in the subsurface. And what we find is that if this angle, so with the convention, it says here somewhere, the convention is always that we draw this angle theta within the most dense of the fluids, water versus gas in this case, or it could be water versus gasoline. This would be the more dense of those two fluids. Then if we measure this angle theta, if this angle theta is less than 90 degrees, then we'd say that this liquid wets this surface. In other words, the liquid tends to run across the surface, and it looks like this nose that is advancing over the surface. If this angle theta was larger than that, so in other words, this angle theta was this, let me do something fancy with a different color, then this would be the shape of the bead that sits on top of it. So instead of this being the lens that sits on top of it, this now is the bead that sits on top of it. Clearly this is larger than 90 degrees, and so this would be a surface that is wetted by the gas in this particular case and not by the liquid. So the difference between the 90-degree one, where both the gas and the liquid equally wet this surface, if the angle is less than 90 degrees, then the liquid wets the surface. If it's more than 90 degrees, then this gas wets the surface. It's just a terminology that's used. But it's important to note Pardon me. It's important to know that because it says something about how fluids will be pushed into the pore spaces of aquifers and whether it's easy to get them out or difficult to get them out. And so this is basically what we said here. If it's less than 90 degrees, then it's water wet. If it's greater than 90 degrees, it's gas wet. And if it's 90 degrees, then it's halfway in between, it's equally. And the ramifications of that are, in terms of kind of fluid mechanics parlance, if you take a capillary tube and you put that capillary tube into water, then you'll find that water rises up in that capillary tube some height, and we know how to calculate that height rise. If this is H2O and this is glass. Glass, by the way, is basically the same as quartz. But if you took a liquid which was mercury, for example, and you did exactly the same by putting a capillary tube into it, what you'd find is that the meniscus would look like this. And it would be depressed by this amount, HL. And the amount of this drop and the concave downwards portion is different from the concave upwards portion. And so this is a glass tube which is wetted by the water. This is a glass tube which is non-wetted by the mercury. And you could imagine that because these things look very different to each other, the behavior of trying to push a gasoline into a porous medium, which is analogous to this tube, would behave in a very different way. So most of the systems we deal with are probably water wet. So they mainly look like this. And mainly look like this. But some systems, like carbonates for instance, where it's not quartz, are the opposite. They're non-wetting to water. And so we'll deal with that in due course. Okay? So that's an important behavior for us to understand. So what we could do, these are just figures that define this behavior. We could, for instance, try and close this. We could look at the behavior of a real porous medium and look at it in terms of these two constraints. One is a water-wet system. So in other words, that's the system that we just drew with a capillary in it, where if we put the capillary inside it, that water would rise in the capillary to some height. And the opposite system is a water non-wet system, where we'd get the opposite behavior. Oil wet. And they look very different. So the picture you're looking at here are some grains in these stippled portions, which are quartz, or some grains. Oil, which is black, and water, which is white. So stippled are the grains, oil is black, water is white. If you start with an oil reservoir, it's mainly filled with oil, and initially it's filled with oil, but it is what's referred to as pendular saturation. And so if you can look at this and you can imagine this, these grains are touching each other. Because the grains want to be wet with water, they have a monolayer of water all over them, and at the points where they touch each other, they have pendular rings which go around them, which are these little triangles. You can imagine these little triangles going around the grain to the other side. And that is a little donut, if you like, which is water, which is in the system. So water touches the grains. It is around the grain contacts in these little donuts that go around the contacts. And everywhere in the big pore space is filled with oil, which you'd like it to be in an oil reservoir, which you can then suck out the fluid. When you produce an oil reservoir, you kind of suck the oil out, but really you do it by replacing it with something. So you suck the oil out and you pump water in, because you have to physically replace what you've taken out. And so if you suck the oil out and replace it with water, then the water content, the white stuff, grows. And it goes from this so-called pendular saturation, as in a pendant that you hang around your neck, dangles, to what is referred to as funicular saturation. As in a funicular railway. Funicular railway is a cog railway where you get carried up the mountain on the top of this railway. So as you take the oil out and replace it with water, what you notice is that if you put a straw in here, all of the oil is connected to every single pore. You suck out the oil from one pore, it's able to come from the pore next door, and it gets pulled out of the system. At some stage after you've pulled enough oil out, then now the oil is no longer continuous between pores, and if you suck, you will only get water out of the system. And you can imagine that's important if you want to get oil out of an oil reservoir, because it'll say something about when you don't get oil out anymore, and you'll leave oil in place and only get water out of the system. If you're trying to clean up an aquifer, which has got an apple in it, black, the oil, then you'd have the same behavior. You'd suck it out, replace it with water, and as you do that, at some stage, you can't get any more out because it sits there as little globs. They're really just bubbles. A bubble of liquid inside a liquid, two fluids that are present, two liquids that are present. And no matter how much of the water you suck out, this won't go. And so that's an important behavior for us to be able to understand something about. If the material happens to be, instead of water wet, which is the case for most of our systems, happens to be the opposite, then it just looks the opposite. And we'd have to deal with it that way. But let's not complicate matters. So this is a fundamental behavior that we have to be aware of. Okay? There's a discussion of this. I think I've talked about all of these pendular rings, wetting phase saturation, and critical saturation. Yeah, I think it's just identified in the pictures. Don't worry about those words. The issue is, it starts off, the continuous phase is oil. You suck fluid out of it, you get only oil. The water is held in place by the fact that it's held by interfacial tension. As you remove the oil and you replace it with something else, you could replace it by oil, or you could replace it by water. If you replace it by water, at some stage, as the saturation of the oil goes down below a critical saturation, all of a sudden the oil isn't connected anymore, and you can't take any more of it out. And so no matter how hard you suck or drive water through the system, you won't physically get this last bit of saturation out of the system. And that's a key issue. So that presumably is going to be important for us to say something about how that happens. So what are the mechanisms by which we can say something quantitatively about how much pressure do we have to apply to push through the system to be able to get these blobs out? What is the limiting saturation by which we can get them out? How do we do those calculations? So the way we do that is to draw on our understanding of Capri pressure. And Capri pressure, in the most simple case, is for us to think about a single Capri tube. And so most of the models that describe a porous medium, so what you could do about this porous medium, you could think about this as being something that has a pore throat in it, which is just the circles which are between the grains. And if you think about these pore throats, you could think about a single one of these pore throats as being a little capillary tube. And to go from one pore to another pore, you physically have to go along that capillary tube. That capillary tube may originally contain oil, and you want to displace it by putting water behind it. Oil in front and water behind. And the question is, what pressure do you have to apply in this direction to push it through? Or if you think about it the other way around, if you were driving something which was, actually the same thing. If you're spilling oil into this capillary tube just under its self-weight, what height of a column of this would you have to supply before it's able to push this thing down? They're analogous questions. And so one way to think about these porous media, this porous medium, is to think of it as a bundle of capillary tubes, where instead of having multiple little pore spaces, you think of a bundle of capillary tubes that you bundle together, and they represent the pore space within this porous medium. And if you can understand the behavior in one pore tube, capillary tube, then you know something about the system. So that's the tack we'll take. And so it's something you've seen before. Take a capillary tube, put it into water. If it's water wet, then the water will rise up it to some height. We'd like to know what this height is. We can calculate that by doing a couple of things, right? Maybe you thought you'd never see this again. You were wrong. What do we know? We know that on any horizontal plane in a static fluid, the pressures are the same. And so the pressure at this point here has to be the same as the pressure here. So we can just cut it off at the base, and this has to be atmospheric pressure on the base of this capillary tube. If we've cut it off at the base and we're holding it, then the force that we have to apply around the top of this capillary tube, so in other words, we have a little shape that looks like this. It has a height which is h sub c. And what we have to do is we have to pull up on this around this circumference, because this is the only place that it touches the edge of this tube. We have a force that's applied. And so what we can do is we can apply a force balance. The force balance is the weight of this which is pulling down, the force on this which is pulling up, and we absolutely know the geometry of this, right? The geometry is going to be equal to the height times the cross-sectional area. This, by definition, is the volume of this tube. So this is the cross-sectional area A. This is the height. And so the volume of this is just the product of those two. And it has a certain unit weight pulling down, which is going to be W, which is equal to unit weight times the volume. You've seen this all before. So this is unit weight. And so this term together is just the weight, which is equal to the unit weight times the volume. And we're trying to hold it up, pull it up by its bootstraps. And the bootstraps are going to be the interfacial tension, which is going to be this force which is applied here. We could think about it being straight up, or you could think of it as an angle. If you think of it as an angle, then it's this term multiplied by the vector component of that. This will typically be close to 1. Maybe I'll make it slightly smaller. And the circumference of this circle is just pi d. So this is circumference. And so if we balance those together, pulling it up by its bootstraps, the force multiplied by the circumference, pulling down is the weight of it, which is just the volume times the unit weight, we have this expression. If we rearrange this expression, we can define the one unknown term that we want to figure out, which is the height rise, which is this. And you've seen this before. It is proportional to the interfacial tension. Double the interfacial tension, you get twice the height rise. It is inversely proportional to the diameter of the tube. Half the diameter of the tube, you double the height rise. And it depends on the unit weight of the fluid, which is in the system as well. And so that's an important relationship. The other thing that we can also do is that because we know that a pressure is equal to a height multiplied by a unit weight, by definition, then we could also multiply this by unit weight, and we'd get a pressure out of it. And so what we could do, if we wanted to, we could multiply this by unit weight W, and then these cancel out, and then this term becomes a pressure. And it's really the pressure that you'd feel on this surface, on this curved surface. And it's useful for us to do that because what we can then do is we can define something called the Capri pressure. And the Capri pressure is just the pressure difference between the pressure in the wetting fluid think water, and the pressure in the non-wetting fluid. Think oil, or air for that matter, in the vadose zone. So by definition, this term Capri pressure is something that's the difference between the pressure that's in the water, which would be the pressure you'd feel in the water there at this point. So let me blow this up. So if you, in other words, if you measure the pressure right here, this would be the pressure in the wetting phase. If you measure the pressure right here in the air, this would be the non-wetting pressure. They're different. It's across an interface. You think that they might be the same, but they're slightly different. And it's that difference which controls the behavior of migration or invasion, if you like, along these capillaries. And so the importance of writing it this way is that if we take this and just multiply by the unit weight, then this now defines a pressure which is going to be 4 times interfacial tension divided by the diameter. And this pressure difference is given by the interfacial tension and the pore size. Have a really small pore size, you can get a very big pressure difference between them. If you have a really big diameter pore, there's essentially no pressure difference. And it's this pressure difference, the Capri pressure, is what drives the behavior of these fluids in the subsurface. Yeah. The Capri pressure is just the difference between the fluid pressures in the non-wetting fluid and wetting fluid. Is that what you said? At the same location. Well, adjacent to each other, right? Not the physically same location. So it's kind of the same location on this surface. If I blow it up. So, whoops, didn't mean to do that. So it's across this interface here, if you can see that, but they're the same point. They're just in the different fluids. All right. So we've said something about that. So an important parameter for us is going to be this Capri pressure. So we'll revisit that many times, but don't forget physically what it means. It's really, the other way to think about it would be, it's this height rise within this Capri pressure multiplied by the unit weight of the fluid. Happens to be the pressure measured different between these fluids at this point, but it's also, well, actually you could think of it as being the pressure within the liquid that you have to pull it up by supporting this as you free suspend this without anything below it. So maybe I'm saying too much about it already. Okay. There's a different way you can think about this, and we won't use this very often. But this relationship called the Young-Laplace equation, and only to make the point that if we wanted to, instead of thinking of a bundle of capillaries, which are all held parallel to each other and have this height rise of the fluid up inside them, we could think about a whole bunch of grains. And with those grains, we could add a small amount of liquid, so that between any 2 grains, there'd be this collar that existed between them, which was water or any other wetting fluid. And so you can imagine that if you have these 2 spherical grains, that there'd be this donut that's around them. It's actually this pendular saturation that we talked about for the wetting fluid. And it has 2 curvatures. It has a curvature which is in this plane here, which has some radius here, R prime, right? So 2 grains, there's a meniscus here, and it has a curvature attached to it. But there's also a second curvature. And if you look in plan view, It's the curvature that goes around here. And so you can't really see it on this, but it would, the curvature, if you like, from the waist that goes around between these points as it goes physically around this thing. And so these are these two radii. And so you can also define the pressure between the liquid and the gas in this particular case as a Capri pressure, which is given by the interfacial tension of the water and the sum of the reciprocals of those radii, 1 over those radii. One being the radius in this direction, and the other being the radius that goes around. And if you add these two together, if you think they're similar to each other, then you end up with an expression which is this. We had an expression before that was similar to this, and I will write it down at the bottom. P was equal to 4 times interfacial tension over diameter, and of course diameter is 2 times radius. And so these are the same expression, representing slightly different things. One, a geometry where you have things which are capillary tubes, where you're trying to push one fluid along and extrude the other fluid. And the other case where you just have these fluids partially saturating this bead pack, of which one representative geometry is just 1 grain, 2 grains on each other with these 2 different radii. But they end up being basically the same behavior. They define a Capri pressure, a difference between the pressure in the gas and the liquid in this particular case. And so that's kind of the fundamental building block that we'll work with. And so now a thought experiment is that if we go back to this previous case, and we think about what's physically going on here. We have a bead pack that has big beads at the top, and it has small beads below this line here. We see that most of this invading fluid has basically stopped at the boundary between these two, and only some of it, actually some of it which happens to be below the highest level of this other stuff here, has actually pushed through on these sinuous pathways where presumably it can find a way to be able to displace the water because it finds a slightly bigger pore space than is present elsewhere. And so that's the behavior that we're trying to define. We've defined it at kind of a pore level, which is useful because it says something about the physics of what's going on. But the other way we could also think about it, and we won't do that today, but we'll do it next time, is we could think about this as being our REV, representative element of volume. And so certainly if we took an REV that was this size, this would almost be 100% saturated with this red fluid because there's only a little bit of water in it. But if we took it at this side, this would only be maybe 30% red saturated and 70% water saturated. So what we'd like to be able to do is to say something about how this saturation will turn out to be if we know something about the properties of this bead pack. And so that's our real task for this. And so one way to think about this would be to do this thought experiment where we take a capillary and make it like this figure here. And so this capillary, I guess, actually I don't know how to do it on its side in this particular figure. Imagine it being on its side. So imagine it being a capillary which is fat and then skinny, fat, skinny as you go down through it. If you tried to push this red fluid through here, it would get hung up on this small portion, and it's not a portion that it can go through. It would get hung up on here and it just wouldn't go any further. It would fill this up really easily because it's very big, but it would get hung up here and it would stop. It's a binary process, a displacement process. It gets hung up and it can't go any further. So if you have a medium which is a capillary which is wide, thin, wide, thin, wide, thin, like this, you get a very specific kind of behavior in here. If you had a medium which was a big capillary and a small capillary next door to it, like this, then what's the behavior that you'd expect? The little capillary, it would go in, it would get hung up, and it doesn't go any further. It's holding it. The big capillary, by consequence, is much more open. It goes in and it keeps on going down, and it would end up at the water table, and it would end up keeping on going. And so the geometry of the porous medium as to what the pore spaces look like as you go from pore throat to pore throat has a big influence on the behavior you'd expect to get of these things invading into the subsurface. And so you can imagine that this behavior that we've kind of alluded to here may actually have something to say about what the architecture is of the pore throats in this subsurface, to be able to say whether when you drop it on the surface it will look like this, or it will look like this, or it will look like the ones here. And so that's clearly going to be something that we're interested in exploring. So one last thought, this very last slide, is what happens if instead of having a porous medium, as we looked at in that previous picture, with the red fluid invading the clear fluid, if we had a fracture in it, a big conduit that was able to allow the fluid to go through it. So instead of having a bundle of capillaries, which might look like this, we had one big physical slice going down through it that we could put stuff into, and it would just keep on going. So in other words, a fracture. Well, we can do exactly the same analysis that we did for a capillary tube, and it is to do the same. We take two parallel plates, we put them in a fluid. If they're close enough together, the liquid will rise up between them, and it's governed by exactly the same physical process, that this will be this meniscus at the top. Same as before, we can cut it at the bottom because it's the same pressure here as we have here, and we can do a force balance. The force balance is a volume of the fluid that we cut off, which is just this red volume here. Height, width, and an aperture. Height, width, and aperture, yes?
What makes the difference in head closer to the tail?
The same as putting the capillary tube. It's interfacial tension that is an attractive force that makes it crawl up the size of the tubes, just like in a capillary tube. So this is the volume. This is unit weight. So together these are volume times unit weight, which is equal to the weight pulling down. And the force pulling up is this length multiplied by the interfacial tension acting along this length. So that would be this length multiplied by interfacial tension. Let's make this 1. And there's two sides of the plate. One side here, one side here. And that's what this is. And if you go through that, we end up with something like a Capri pressure. Well, we get a height rise first, which I guess we can calculate, which is proportional to the interfacial tension and inversely proportional to the separation. So if they're widely separated, basically it's 0 height rise. If they're very close to each other, it's a high height rise. And if we multiply this by unit weight, then this becomes a pressure difference. And it's this Capri pressure, which is very similar to the one for Capri tube. So we said before that for a Capri tube, what was it? It was Capri pressure was equal to interfacial tension times 2 times the radius, I think, right? Just about it. 2 times. Thank you. And we're left with this magnitude, which has the same proportionality. Question? Okay. And so,
You go through the fluid is going through the fluid, and it's like that weird shape that's going in and out, getting smaller and smaller. It comes to a complete stop, or is it Just slow down.
It comes to a complete stop. It goes up to this height rise, then it stops. And so this is the equilibrium behavior. And so what we've been able to do is to be able to say something about, we'd like to be able to say something about what are the controls on whether this stuff can get into the pore space or not. Whether it's pore capillaries, which are very small, or fractures, we now know something about what the controls are on whether it can invade or not. And so what we will do next time is we'll try and say something about what the behavior would be, not at an individual pore scale, actually I want to look at this one, but what happens at the scale of a portion of the aquifer. So how do we use what we know now to be able to say something about whether this portion of the aquifer would be 100% full with the red fluid or 0% full of the red fluid? And we'll deal with that next time. Okay?